Hey everyone, this is a super long video about the tscircuit Autorouter. After this video, you should have a general sense of how the tscircuit Autorouter works and how to dig into the code base. One of our goals is we really want contributors for this Autorouter, so if you're interested in that, definitely hop on our Discord. The link will be in the description. I would also highly recommend if you are dealing with an Autorouter or you already have an autorouting problem, just go to the sections that are relevant to your problem failing. Inside the docs, you can look up the report an Autorouter bug doc that'll show you how to use the debugger to figure out which phase of the Autorouter might be causing a problem for you. The Autorouter does a ton of stuff. Some sections are longer than others, so definitely skip around or click to the section that's most relevant. There's also a lot of unique things our Autorouter does, or a lot of sections that people tend to be more interested in. There's mesh construction, and there's sort of like high-level pathfinding, and then there's low-level pathfinding, and then there's post-processing and all this stuff. So enjoy the video, but definitely go to YouTube and click those timestamps at the bottom to skip around to the relevant sections. And with that, we'll begin. Before we jump into the specifics of the Autorouter, I just want to show how you can quickly open problems up in the autorouting debugger. So if you go to any tscircuit viewer, and you run the project, you route the board, whatever. Even if there's no error, you can go to the errors tab and hit open autorouting log and then report bug. And this will open up a URL where your autorouting problem has been uploaded. And then you can download this bug report, and there's a whole guide on how to sort of get these loaded into the debugger and reproduce for autorouting maintainers and stuff like that. But you can also hit open an autorouting debugger and kind of open it up and see the autorouting process run for any problem. So that's a really quick way to debug autorouting problems. In this video, I'm going to talk about the first phase of the tscircuit Autorouter. If I scroll down, I'm in the E2E3 example, end-to-end 3 example. So we're just doing an end-to-end circuit board routing. And we can see there's all these stages, and maybe this will change by the time you see this video, but there's lots of stages. Like we introduce new ones all the time. If I hit solve completely, we can see that we've run through every stage to solve this board. And then I can hit filter by step, and I can step through each phase. We're just going to look at this first phase in this video, the net to point pair solver, also minimum spanning tree phase. So what this phase does is it says, it looks at a net, and we'll step through this whole thing. So I'm going to refresh this page, and I'm just going to step, and we are now inside of the net to point pairs solver. Okay, I'm also going to hit deep viz, so if there's any sub solvers, we'll see the sub visualizations. So what it's doing is it starts with all these traces, and you can see like these 3 right here. So this one, and this one, they kind of are all connected, but it's not clear what order you should connect these things together. We have a little bit of a traveling salesman-esque problem. And the whole point of this phase is to look at these nets of points we want to connect, and then go, okay, let's turn it into pairs. It's a lot easier to figure out how to route things when everything we're routing is just routed by pairs. So if I hit step and I start going through the iterations, this solver doesn't show too much debugging, but it converts those nets into pairs. Okay, so now there's no line between this MST2 and MST0, if these 2 points, there's no line between them anymore. We've consolidated it into this blue line. So if I refresh the page, hit step, okay, so here we have a red line doing all of these, and then we hit step, and it consolidates into this blue line. So that's really what this is. We're consolidating into pairs. I can keep stepping through it until everything is consolidated into pairs, and that is the net to point pair solver phase, also known as an MST. If you look at the prefixes here, oh, I guess yeah. So Some of these didn't, like source trace 3, I guess is what this is called, source trace 3. For whatever reason, the minimum spanning tree wasn't used there. I don't know why, but you can see that when the minimum spanning tree is used, each of these, their IDs change for these points. These are the points to connect inside of the simple route JSON. They change to just say what their index was in the original minimum spanning tree. So not much meaningfulness behind that, other than you can kind of tell that something was simplified via a minimum spanning tree. Okay, let's look at the code for this. I'm going to open up the Autorouter repo code. You can see I'm doing a blog post. And then we are going to look up the net to point pairs solver. Okay, so now we can look at the input to the solver. So it takes in a simple route JSON, our kind of standard input for the Autorouter. You can take a look at this, but it's very, very simple. We have all the connections we want to make, and we can look up the connection object. We've got a bunch of points to connect in there, so that's what we were looking at earlier. And we've got the bounds of the problem. We've got traces. So traces are actually an output. So the reason why this question mark is there, it's undefined initially. We have obstacles. Obstacles are also very important. We only support the rect obstacle at the moment, at the time I'm recording this, but they're not really involved in this minimum spanning tree phase. We're not worried about obstacles yet. So we're really just taking these connections and turning it into point pairs. So what is the output of this phase? Let's see if we can find the output. Get new simple route JSON. So I think what we do is we return new connections that are composed completely of point pairs. And I can see we're building a minimum spanning tree. So I don't know if okay. So in the new connections, it's always a pair. So we're making sure that all future connections are only pairs. For whatever reason, that makes it easier. You can already kind of tell that this could be a problem in some contexts. Like maybe you don't want the minimum spanning tree sometimes, because actually taking a detour around the board might lead to a little bit of an easier path. Like let's say there's a lot of congestion in one part of the board. You might want to take a longer path to avoid congestion. Like this part's pretty packed relative to over here. It's pretty spacious. So that's how the net to point pair solver works. Maybe I'll point out, if you look at the auto routing pipeline solver, you can see that's where all the solvers are defined, and we can see the pipeline step. We can kind of tell what we do when it's solved. We do the simple route JSON SRJ with point pairs. We use that output. That's basically the only real output. I think these are color annotations, and the connection map, we're just updating the connection map because some of these IDs changed. Connection maps are super useful to quickly tell if two things are connected. Connectivity maps. So it's a very standard data structure in tscircuit. The connectivity map, you just can say, hey, are these two things connected with it? So after the net to point pair solver, there is a node solver. So we'll talk about that in the next video of that value. So that's kind of the value that it gets down to. And that's why we don't have nodes, too many nodes less than 1. If your capacity is less than 1, that means that a via cannot fit inside of you. And because a via cannot fit inside of the node, it is made into a single layer node. So if I zoom in here, you can see I can hover over 2 different boxes, and the boxes are kind of sort of like a jar a little bit. They're actually on the same point, but they're just broken up like that to kind of give this impression of a 3D view, okay? So one of these corresponds to the top, the other corresponds to the bottom. And if when I'm hovering over this, you can see it says available Z equals available Z 0. So that means it's on layer 0. If I hover over the other one, it says available Z 1. So that means it is on the bottom layer. In this case, for a 2-layer board, available Z 1 is the bottom, available Z 0 is the top. But that can go up to 4 and stuff like that. So, or 4 or 8 or whatever. So we're creating 2 nodes here. If we look at the available Z for a gray node, you can see it's 0 and 1. So you can go between layers because you have a via. A via is a hole that basically a wire goes through. Okay, that's probably the easiest way to think about it. So you can go under to the other side. You can go up and down, and you have to have some via capacity to be able to do that. You can also see we have red nodes. You can see OBS true or obstacle true for these nodes. So no traces are allowed to go there. And I believe that's it for this node solver phase. So we have a single layer kind of squares. If you look very carefully here, you can see this is a single layer. Actually, you can tell in a couple places. I guess this is worth pointing out. Near an obstacle, sometimes we just say obstacle true, nothing can go there. But sometimes, as in the case with this obstacle, we're saying something can go there, but only on the bottom because there's obstacles on the top. And when you hover over an obstacle, you'll see it has a Z. It can also have multiple Z. And that means that it's only on the top. Okay, so there's an obstacle on the top. Maybe there's a chip on top of the board or an SMT pad, so something that uses copper, and it's just blocking any trace from going through there. No wires can go on the top, but wires can go on the bottom, which is why you have this obstacle. And there's you can see I can't hover over them, but there are nodes on the bottom. If you do want to be able to hover over those nodes, there's usually a filter, but the filter option isn't working on this visualizer. So. And both layers are blocked here. So this obstacle covers both layers. That is common with a hole. So if you have a hole, then there's no way to route on the top or the bottom. It's completely blocked. So that is probably a hole. So you got to remember what the what the physical analog of these obstacles is. And I guess maybe I can show this just to give this a little bit more meaning. So we're not going to go through these phases right now, but you can see that a graph is eventually constructed to wire these nodes together. So these nodes become the foundation of our global routing problem. So we solve global and then local or sometimes called detailed routing. So we solve high level, like generally where is this trace going to go, and then we solve the low level stuff. So yes, here is an example. So we cleaned up the nodes a little bit. We got them closer because for this visualizer, it's helpful. But yeah, in the later stage, in the initial pathing solver, we get some initial routes that maybe our traces could take, some global routes, and they go through these high level nodes. These nodes are super important. You'll see that they're used in a bunch of places, but eventually they are used as small routing problems where we try to route inside of a node. So if we have multiple traces in a node, like in this case, we'll try to route those traces in the node. So if you're interested in that phase, that's the high density routing phase. Okay, so the high density routing phase is what routes inside of a node, or we also call it an intra-node solver. And then this global phase, the second phase here for the mesh, this is just getting the node started. So see the videos on those other stages if you're interested in that, but that's what the mesh node or capacity mesh node phase, the node solver in phase 2 does. In the last video, I talked about conceptually what this node mesh phase does. For this next video, I'm going to animate through the mesh solver so that we can start to understand how this solver works, and we're going to look at some of the code. So this is an animation of the mesh solver, and at a high level, that played very quickly. But at a high level, what happens is you have this node, and you say, does it contain an obstacle? And I'll just step through it. And if it does, then we break it down into smaller nodes, and we see if those nodes contain obstacles, okay? So in this case, we're saying, okay, does it contain an obstacle? And something that's not really shown here is there's also a boundary of the board, which would be an obstacle. So it's not shown in the visualization, but there's a board boundary. So that's why this one broke up. But you can see it tested all the children, for all the subdivided children, if they contain an obstacle. These ones didn't, so they're done. Once you're gray or a blue or this purple color, you're done. These ones, it said, oh, I'm still outside the board, so I'm going to subdivide again. It's going to subdivide again, and then it's finally finding some end state for those. So these ones are all on the boundary, which is a little confusing, but these ones are not, so this is a little bit more clear. Okay, so that one's on the boundary. So it's breaking up that. Okay, so this one, we have two obstacles here. And we can see it's slowly breaking them up. It's creating some blue nodes behind this because on the bottom layer, there is no obstacle. So it's breaking it up. I believe when it's fully contained, it breaks it up so that it breaks it up into two separate layers. So nodes on two separate layers when it's fully contained, so that it can create those single layer nodes. And you can see the process is executing. So that's basically how the solver works in a nutshell. You can animate through the entire process and sort of get a sense of how it operates, but pretty straightforward. And this is the next phase, so don't worry about that. Okay, so this is our output, right? Let's take a look at the code for this because everything's pretty confusing when you from the animation. I want people to know how to dive into the next step. You might find that there's really no problem in this phase, or you might find that there's a big problem in this phase. For example, maybe you need to support circular obstacles. That would be a reason to dig into this phase. In our pipeline definition, in the auto routing pipeline solver, and this is really where everything begins, we can see the point pair solver and then the node solver. So this is called the node solver, a node mesh solver, a capacity node solver. All those names are kind of the same. And what we pass in is to the solver. This is the second argument here is to get the constructor parameters. We're passing in the simple route JSON, and I think that's basically it. We're really just passing that in. There's some hard-coded parameters like via diameter and obstacle margin here. So obstacle margin is the number. These are all in millimeters, by the way, standard unit. Obstacle margin is how close can I be to an obstacle? If I'm within 0.1 millimeters, that's a little too close. So 100 microns is a little too close. So we're just setting that limit. You can see there's all these tests to determine is a node kind of in it or in an obstacle, and it's also setting up some things. Contains target means it contains a point to connect. A target is the same as a point to connect. A point to connect in simple route JSON is just one of the points that you're going to be trying to connect with a trace. Sometimes our solvers are enumerated. So you can see the one being used here is capacity mesh node solver 2. They're enumerated when we're trying out different techniques, and maybe we want to go back to the old technique. I think all the enumerated ones extend this kind of general class. So if you're trying to get a sense of how this thing works, and all of our solvers kind of have this step function, which is a good place to start. So you can just think of this step function being repeatedly called. We can see it's a little bit of a recursive-ish implementation. So we have this next node from our queue of unfinished nodes, and we look at that node, we get its child nodes, we check if we should subdivide based on the child nodes, and then we add the unfinished nodes to the finished nodes. So even though there's a lot of functions and stuff like that, it's pretty simple, and it's actually pretty intuitive if you look at it with the animation. So if I animate it, it's pretty intuitive. So these red nodes are the nodes in the queue, and then I'm getting the children each iteration and checking them. You can also see that the next node, I believe, is always highlighted in orange. Okay, so that's also how to create a good visualize function. If you look at the visualize function down here, this is the thing that's creating that nice visualization for us. It has some logic for selecting next node. So if you're building new solvers, definitely throw in some function like that, or throw in some part of your visualization that tells you, okay, what's the next thing I'm doing? That's very helpful for understanding the algorithm. I don't know why we extended nodes under obstacle. So I guess we're adding nodes under obstacle support. It looks like the step function has changed, and a lot of stuff has changed for the revised version. But conceptually, still kind of the same thing. It looks like the difference I'm assuming the difference is we're doing Z subdivision. So when sometimes we try to break up into layers. So I guess the original didn't break up into layers, and this one breaks up into layers. So that would be the big difference. And I think that's it for the capacity mesh node solver. The main reason to dig into this would be like, I want to change the sort of initial topology of the nodes. Sometimes we can change the topology with subsequent phases. So there are phases that simplify the node structure. For example, we kill dead ends. You can identify if a node is just totally a dead end. So you can modify the node structure in a future phase, or you could say, look, I really want a completely different basis to start with, and that's why you would modify this phase. Good luck. Okay, we're going to look at two stages together now, single layer node merger and the straw solver. So these are two phases that kind of take this mesh network that we've constructed here and simplify it. Okay, so I'm going to step through these very quickly. So the first one is node merging. Okay, node merging kind of does what it says. It merges nodes together. That I think it might be doing only single layer node merging. So I think it merges single layer nodes together, and we'll take a look at the source code and confirm that. But it does this kind of node merging to simplify the graph. So let's take a peek at that again. So before there were a lot of nodes under here, but then there are less now. So I wonder, maybe I can, yeah, we can step back and forth with this step selector. So we can see in the first mesh node solving phase, which my last video is about, we have tons of these small nodes, and then we have a lot less. So the first thing we do is we merge them all together, and then we actually break them up again, or we change them in a subsequent phase. So I'll go over that phase now. The next thing we're going to do is a straw optimization. Okay, so this next phase does the straw optimization. What we realized, if we look at the original mesh nodes here, what we found is that traces would tend to go through these areas, and because they're single layer nodes, the trace would cut off any other trace from being able to use that area. So it would cut up this usable area. And the most efficient way most of the time to go through these center parts is in a straight line, or if all the traces that go through this go in a straight line, right? So this should be pretty easy to kind of illustrate. If you have traces kind of going like this through an area where they're not allowed to cross each other because it's single layer, the most efficient way is always going to be for them to be parallel. Let's say we're going through. Let's say this is the area we're going through. Going in non-parallel lines isn't going to be very efficient. Maybe I'm over here and I want to get. Let's draw a different color. Maybe I'm a new trace. I want to get over there. I'm kind of stuck here because all these guys kind of cut me off, right? So when you don't have straight lines, or you don't have lines that are strictly in parallel, they don't make efficient use of the space. So what the straw solver does is it says, I'm going to pick a direction. So this is a straw solver. It says, I'm going to pick a direction. It's either going to go, all the traces are going to go this way, or all the traces are going to go this way. I'm going to pick a direction. I'm going to create nodes that force any trace that enters that node to go straight through it. Okay. And this not only is better for space utilization, but it can also greatly simplify the problem of the trace solving problem, because it reduces the number of edges. So each of these nodes has 4 edges, right? It connects to tons of nodes beneath it and stuff like that. When we do the straw solving, these do not even connect to each other. So this would connect. Let's see if we can actually go to that edge phase. Yeah. So if we look, this is now the edge solver phase. That's the subsequent phase. We can see these straws don't connect to each other. There's no line from here, from here to here. There's no line from there to there, right? So I can, if I'm this straw, I can go up here, over there, but I can't go down here. So all the traces are kind of forced to go in a straight line. They're not allowed to take up that much space within the node. So let's go back. So we pick a direction and we create straws for that direction. A lot of people have identified that there's often problems with the straw phase because it does kind of force a particularly opinionated approach onto the problem. And you can see kind of in this section, it's a little bit weird, right? It's you know, maybe you could shove two traces in parallel along this thing, but it chose a vertical direction for that layer. So there are many times weird things that happen as part of the straw phase, but yeah, this is definitely an active area of development, making sure that these nodes are very well formed so that you don't run into issues. But single layer drawing is very difficult when you have to route on a single layer, because you're not allowed to put in a via to kind of solve a problem. So it's a little bit difficult to solve that problem. But anyway, this is how we sort of manipulate the graph. So before these two phases, before the single layer node merger and the straw solver, those are the two phases we're talking about, 3 and 4. We have this problem. We've got this very big graph that looks like this. It looks kind of nice. And then we reduce the nodes dramatically by creating these straws. And as part of kind of figuring out how to create these straws, we combine all these nodes together into groups. We merge the nodes together to know how to best create those straws. And these straws are also considered in future phases. So for edge construction later, we say, okay, you can't travel between two straws on the same node to try to keep that density as high as possible on that single layer between straws. So those are the kind of graph capacity mesh node optimization stages. Yeah. Okay, in this video, I'm going to talk about this edge solving phase. So after we've simplified the nodes, we've talked for a couple videos now about generating nodes and creating straw nodes. You then need to create edges between all of these nodes to construct a graph. You don't have a graph without edges, right? At least you don't have an interesting graph. So that's what this fifth step, the edge solver, is all about. We're going to create our graph by drawing edges. So I'm going to animate this phase. So I'm going to go right before it, and I'm going to hit animate. That goes pretty quick. Sorry, now we're animating through the entire algorithm. But yeah, let's do that one more time, except maybe what I'll do, whoops, it's hard to get it right. There's actually a play button next to each phase at the bottom here. So if you ever want to get to a phase, you can hit that play button and just go up to that phase. I'm going to quickly stop that animation. So this phase is pretty simple, and I can't imagine what could be wrong with this phase. Maybe we'll find something, but you can see it's just going through each node. It doesn't really tell you which node, unfortunately. Maybe the deep viz will tell us. Yeah, it's not really telling us which node is next, but I can kind of get a sense of the order. And it is just looking for any nodes that are adjacent to it and drawing edges to those nodes. So pretty simple. I'm just saying, hey, what nodes are next to me? What nodes can I travel to? And then adding edges there. So you have to consider the layers. If you hover over anything, you can see available Z01. So that means it can connect to the 0 or 1 layer. You can only have edges between things that have a shared layer. If they don't have a shared layer, you cannot connect them. You can also see the edge solver is not drawing edges between two straw nodes, and that's to keep the density on for these single layer straw nodes very, very high. Okay, so it's a little bit opinionated in how it solves for edges. Less edges is also good as an optimization. If you have a lot of edges, you're going to go a little bit slower. Yeah, and when you see things like this makes sense, right? So what it can travel to straw nodes on either of these. It's adjacent to these. It might look weird that there's only one line to this other node, but that one line, it's not, the stroke width isn't drawn proportional to how much it can carry. A lot of traces can go under there. There's a connection between those nodes, and that connection can carry many traces between those two nodes, but it's only drawn as a thin line. We can look at the code for this briefly. We can see the name of the solver right there, capacity mesh edge solver, node tree version. So this is another solver that seems to have multiple versions. Uh-oh. Let me copy that. Do a search in the project. So we can see it takes a bunch of capacity mesh nodes in as input. Capacity mesh nodes are very simple. They have a center, a width, and a height, and available Z. So that's what shows when you hover over them. Throughout the render phases, we actually mutate them and add a bunch of extra stuff on. So some of these it starts with, you're not always guaranteed that these are going to be on it. I think these are all set at this point, by this point. One of the important ones is straw node. So we now know that the capacity node is a straw node, and we can have logic specific to that. And we also track the parent of the mesh node, which is, it can be very important because for knowing what it could possibly be adjacent to. You can kind of look at it like a tree. Let's see. How does this actually work? We get nodes in an area using a node tree, and the node tree, if I had to guess, is probably an optimized. This is a spatial hash index. So what that means, it sounds complicated, spatial hash index, but it just means that it has a way of hashing the coordinates, the rounded coordinates, into buckets. So it's very quick to find things that it's close to. And this phase executes very quick. So in general, when you're looking at these phases, you can see the amount of time to execute. Because I'm animating this and taking forever to explain this video, this phase looks like it's taking a while. But if you hit solve completely, you'll see that this phase executes very, very quickly, especially relative to the Unravel solver, which is a very complicated solver. This phase is not bad at all. And you can always do filter by step to kind of jump to that phase without worrying about the animations or anything like that. So what else is there to say on that? What's the phase after this? Is there anything? So dead end solver. So that's just solving for paths that we would never ever want to go down for some reason. And then initial pathing solver. So all these edges are going to be used by the initial pathing solver, which just finds this kind of general route through these nodes. It might not be the perfect route or even the final route, but it's an initial route that'll later be optimized. So that's what these edges are for. Yeah, I think that's about it for the initial path, the edge solver. We're just looking at adjacent nodes. We're just saying what nodes are around me, and then creating edges between them. If we look at the output of this, it doesn't say because it's probably in the parent class. Let's see if we can find. Yeah, so each step, we can see what it's doing each step here. Let's see. There's our visualize function. I don't see what this outputs, so I can go to the auto routing pipeline solver, it looks like it replaces the capacity, or sorry, wrong phase. Edge solver, capacity edges. Okay, so it sets the CMS here is the I don't know why it's called CMS, but CMS auto routing pipeline solver. It's the main solver. I don't know why I don't know why this is written as CMS. But it's setting the capacity edges of the problem. So I think these are the edges that will that'll basically stay here until they're, I guess in the next phase they're replaced. If we determine that something's a dead end, we shrink the graph. But yeah, this is just the phase where we set up the edges. Okay, so the dead end solver. We just talked about how we construct meshes, and now we're talking about the dead end solver. Solving for dead ends is not as simple as you might think. Like for example, up here, are these dead ends? If you look at the, let's kind of flip to the solved problem here. You know, if you had a node like right here, would that be considered a dead end because it's not really between anything? We wouldn't consider that a dead end. It might be used somehow. Like a node right here, even though there's nothing connecting here or right here, those might not be dead ends. There could be something connecting here. A dead end solver the dead end solver, which is stage 6 here, it has to know that definitely a node will not be used to remove it. So we're going through these stages, and we've got all of our edges, and we want to know which nodes we just do not need. A dead end is a node. I believe these are dead ends over here. A dead end is a node that there's just no reason to take it. It just cannot possibly be taken. And I believe if we flip between these stages, you can see some of these nodes fading out. So this visualization is tough. But you can see at least this one is fading out. And I believe that means that it is considered a dead end node. So that this visualization stage will need to be fixed. But generally a dead end node, it's just, it could not possibly help. So, oops, wrong way. Sorry. I think it's stage 6 and 7. Am I crazy? Oh, I flipped too far. Okay, they're 5 and 6, because it's 0 indexed. Okay, so I'm just flipping here, and we could see that this node is fading out. I believe that's correct. Like that one could be a dead end. But anyway, you have to be overwhelmingly sure that a node cannot be used. So let's take a look at the code for it and see if we can figure out the dead end solver. This is one solver I didn't personally participate too much in the writing of. I can't remember, but I think, yeah, it looks like it's just using the edges and an adjacency list to find where something is, if you think of like kind of like a tree, it just could not possibly connect to some other node. So I'm gonna avoid going into the code details yet for that one, and I'll probably have to redo this part. But the dead end solver is basically just for getting rid of edges that are definitely could not be used. They just could not possibly be useful. Okay, this is very exciting. The next phase we're going to go into is this initial pathing solver. And why this is exciting is for the first time we will be using a conventional routing algorithm. We will be using A-star for the first time. So if you're not familiar with A-star, there's a great NPM package, I believe, that gives you an A-star visualization. I think it's called Pathfinding JS. And we don't use this package, I don't think, but I love the visualizer they give you. So let's see if we can get this visualizer working. So I have A-star and heuristic Manhattan selected, so Manhattan distance. And I should be able to run this somehow. Maybe I made my screen too small. Yeah, start search, and we can see all the nodes it explores to get somewhere. Now, we are a topological autorouter, which means everything is kind of topological, but when people say topological autorouter, they typically mean we first figure out the optimal topology and then we solve. So we don't have a grid-based topology, but we can still use A-star, because in A-star, really it's a graph search algorithm. And it just says that all of these kind of adjacent tiles are next to each other. So you don't need to use A-star with a grid-based graph, and we don't use it for a grid-based graph in this case. So when we look at the result, let's start with the result of the initial pathing solver, we get point-to-point solutions for what nodes to go through. And these nodes are also ostensibly the shortest way to get to a particular destination. Shortest, and they avoid overloading the capacity of a node too much. If you've ever used A-star before, you'll know there are 3 parameters to keep track of: G, H, and F. Okay, and G is the cost, H is the estimated remaining cost, and F is the sum of those two. So really G and H are the 2 things you're going to worry about. And the thing to keep in mind is G is typically a very good cost, a very well-known cost, and then H is usually an approximation of remaining cost. Okay, so that's just some A-star basics there. And what we're going to do is animate this phase so that we can understand it a little better. So what I'm going to do is scroll down here, and I'm going to hit, I think I can hit play to go all the way to that stage. And then I'm just going to hit the, I'm going to hit deep viz, and then I'll just take a couple steps here. And I think we can see the A* Autorouter in action. So if I animate this, it'll go really quick. So I'm just going to go step by step. Okay, so we're solving for the path between these two nodes. Okay, and if I hit step, you can see all the places that are queued to be explored with these orange lines. Okay, so those are all paths that are queued to be explored. And as I hit step here, it's exploring until it finds the full route. That visualization is not so great. But it worked very quickly. But this solver phase, unlike many other types of auto routing for A* solvers, it's very greedy. You can even see the name of it is capacity pathing greedy solver. So the reason why this is called initial pathing solver is we will optimize these routes in a future phase. Yeah, I think what's happening is the orange lines that show the next candidate. Oh no, now they're blue. But I think they're quite faded, so it's a little bit hard to see which one it's currently on. So this visualization could certainly be improved. And I also want to say these faded blue lines are showing the most promising candidates. When I hover over nodes, I can see that the G and H values have been populated. So I can see G is 21, H is 3.48. So H is the remaining, the estimated remaining cost, and G is the total cost to have reached that node. So the sum of this line so far. Okay, so that's how G and H kind of work there. And it just solves them all in any order. The initial pathing solver is a bit stupid in that it doesn't really care what other traces have done. And you'll see that this is the biggest problem in auto routing. Trying to figure out what order to route traces and how much to have those traces interact. You'll see things like rip and replace and stuff like that. We don't do rip and replace for this auto router, but I'm not sure. Maybe with the greedy pathing solver, we add some additional cost if there's a lot of traces within a node. But something I also want to point out is that these nodes all have capacity, right? And so many times we'll penalize if a path goes through a node that is at capacity, right? If it doesn't have space, we'll say, hey, don't take that node, or we're going to associate a cost with that node. Explore something else. Explore something else first. So, yeah, that's basically the initial pathing solver phase. In the next video, we're going to kind of talk about how we optimize these initial routes. But yeah, this is part of the optimization phase, which is the next one. But the initial pathing solver is really just about finding those initial routes from our edge network. And now we can start to operate and figure out how to optimize them and maybe get a little bit less density out of it. But that's basically how the solver works. Okay, in this video, we're going to look at how the code for the capacity or the initial pathing solver works, which I guess is a type of capacity pathing solver. So again, it's the thing that takes a pair of points and kind of runs an A* algorithm to connect those points together through these nodes. And when we went over this last time, we could see that there was on each node being explored, there are this G cost, the heuristic cost, which is an estimate on the remaining cost, and then the F, which is a weighted sum of those two things. So really just G and H is all you need to worry about. And so G means, the sum of all the costs that have come before, and H means the estimated cost of the future. So that's going to be important. I'm going to jump right into the solver. So the solver used in this phase extends this capacity pathing solver. So this is kind of a base class for all of them. You can get the actual solver class just by looking at the active stage in here. So, if I refresh this, I go down here, hit play, I can see the active stage. I can also hit deep viz and step through it to see if there's any subsolvers. I don't think there's any subsolvers being used. Let's go. Whenever you're looking at a solver, just go to the step function. It's the easiest way to go. I was looking at this earlier, and this is a misnomer, so I'm just going to rename that right now. So we have a current connection. So we're just looking at our current connection, and as we go through them, we'll increase that index. So we're looking at that current pair, right? So there's this red line. So this is the current connection that we're looking at. And we've got a list of candidates. I guess that's handling for if we don't have the list yet. We're sorting the candidates based on F. So we're hitting the candidates with the lowest cost first, or the lowest estimated cost, because it's G and H together. We get the next candidate to evaluate. So this is in this case, I don't think it shows current candidate, but let's pretend that this is the candidate. What we're doing is we're saying, okay, let's take a deeper look at this candidate. Let's see where this candidate can go. Maybe we're almost at the end, right? So you're just doing that kind of A* exploration. Again, if we look at pathfinding.js and we animate this, can I reset? Oops. Whoa, no. I don't know how to, sorry about that. I'm leaving it in though. If I start search again, it's like you always have one square you're advancing at a time. Even though it goes very fast and it seems like it's expanding evenly, you're always really looking at one node at a time, and that would be the next candidate, the one that has the highest ROI, the one you think is closest to the end or has the lowest cost. You're going to look at that. So this could also be called the best current candidate, right? This is the one we think is closest to the goal, is the right way to go based on those cost functions. So we get that current candidate, and then we see, okay, is it connected to the end? If so, we're done. If not, we're going to get the neighboring nodes and add them to our candidate list. So try to expand outward further. And this is how basically every A* solver works. But this one, it has, and I think in this repo, all of our A* solvers work like this. We have a compute G and a compute H function, right? And so compute G is always going to compute the cost of the path so far. And then compute H is always going to estimate the cost into the future. And then here's our calculation of F, which is a weighted sum of these things. So this greedy multiplier is a hack to make A* act less optimally, but go much, much, much faster. Okay, so you don't really need to worry about that. If you're familiar with A*, a lot of times they don't teach this kind of concept of a greedy multiplier. It's called many different things. It's called weighted A* in many cases. You can completely ignore this, other than it makes A* go faster and on occasion not do something optimal, but usually it ends up being optimal anyway. And there's actually a bound of how non-optimal it can get. So it's a very good compromise if you want to go fast. Lots of speed increase and very low decrease in optimality. So compute H is kind of the interesting function here. How do we compute how much estimated distance there is? And in this case, for this base class, we just compute a simple distance for the between the nodes. And then to compute the G cost, we just say, okay, what's my cost to the previous node I was at, and add that to the cost to get to that previous node. So very, very simple G and H functions for this kind of graph exploration. And I think the actual class being used is this thing called capacity pathing greedy solver. So it looks like this solver really only differs in that it always, so there's a function, does node have capacity for trace, which presumably is just a check, and it's saying I always have capacity. So this solver, because in the initial pathing phase, we don't really want to block any solution because they'll be optimized later. I guess we found that just saying, hey, it doesn't matter if a node doesn't have capacity, let it through is a good option. You could also override this function to say, hey, if the capacity is getting too negative, like we really, really don't have capacity, you could return false, but then you risk never finding a solution. And I think with the initial pathing solver, we just always want to get a solution. It's an approximation, because in the next phase, we're going to optimize that path. If we scroll down, in the pathing optimizer will optimize those paths. So it's not really that big of a deal to get a bad path. We'll optimize it. Get node capacity penalty. I guess that's a way of getting a penalty, presumably to the G, to the G and not the H, but I'm not sure how it's used. So we're penalizing based on the node capacity in some way. So maybe this biases it to kind of explore routes that don't go through other nodes. So lots of ways to kind of tweak this to get good initial paths. Having good initial paths speeds up later phases paths. But basically, in a nutshell, that is how the initial pathing solver works. In the next stage, we'll talk about the pathing optimizer in the next video. Okay, in this video, we're going to talk about the stage after you've optimized the paths. After the pathing optimizer, our high-level paths are essentially finalized. So we've basically figured out, okay, this is the high-level path we want to take between nodes. So the next stage, if we go to it, is going to determine how we enter and exit those nodes, where we enter and exit, and what layer we enter and exit on. So this is almost like a logistics phase, not much to worry about. The point where like it's easiest to just look at it from the previous phase to the next. So it's tough because you don't see the circuit in the background anymore, but you can kind of tell if I flip quickly between these two phases, we're basically saying, okay, we need to go from this node to this node. Where do we enter and exit? And if I hover over this, we can see, okay, we're gonna enter or exit on either the 0 or 1 layer, available Z, and I'm source trace 6 and stuff like that. So yeah, just where do I enter and exit on the nodes? It's a little bit confusing, and I'm probably not going to go into the code too much for this one, but there's kind of two stages, edge to port segment solver, and then segment to point solver. Okay, so the next one is more important. I think this one might be more focused on just what edges. So you can see like when there's nodes that border in a weird way, especially there's like a lot of distortion here from the presentation. We need to figure out exactly where in physical space to the millimeter, to the micron, where we're allowed to enter or exit. So this first phase, the edge to port segment solver, finds port segments, and we're basically saying, okay, we can enter or exit anywhere on that segment. The next phase, so step 10 here, figures out where the specific point is that the trace will enter or exit. And I think it might also, no, we still don't know exactly what layer, but we know exactly the X and Y coordinate of where the it'll exit or enter. So that's it. So we're now getting from abstract kind of global space into the low level physical space. And this is to set up for this high density solving problem where we solve for the specific routes inside of here. It's all just set up for that. And you can see we kind of know where we're going to enter and exit physically in each node. There's a lot of interesting things you can do with this phase that we don't currently do, at least at the time of this video. For example, these are closer than they need to be. If they can be anywhere on the segment, so they could actually be pushed a little bit further from each other. And you might want to do that if you're routing power or something like that. You might want to push them a little bit further apart. But we're starting to move from this kind of abstract high-level space into the low-level space, so that's good. And the next phase is the unraveling is a very unique phase that I'm excited to get into. Okay, this next phase is very exciting because it's very unique. This is called the unravel stage. And unraveling is a technique I had never heard from anyone. I was desperately trying to improve the performance of the Autorouter and came up with this idea of unraveling. What unraveling does is we say, we want to determine the exact layer of, so we're looking at the output of the unraveler right now, and we want to determine the exact output layer for each of these points along a trace. But when we select a layer or the position along the segment, we create crossing, and sometimes same layer crossing, which necessitates a via. We have to burrow under. So there's all these wires crossing, and we want to unravel them or unwind them such that they cross as little as possible. And the reason we want to do that is to decrease the node probability of failure. So the visualizer on this one is a little bit weird, but this square in the center tells you what the node probability of failure is. And it's pretty low there. It's like 4%, 0.04. But why would it be, what's the risk, right? You have to imagine, it's kind of tough, but you can kind of get a sense of the overall size of the node. It doesn't show the bounds of a node, unfortunately. But why would there be any risk here? And with the unraveling stage, fortunately or unfortunately, it has this kind of like syntax to the lines. Each line is drawn very peculiar to communicate something to the algorithm debugger. So a dashed line, a sort of uniform dashed line means it's on the bottom layer. A solid line means it's on the top layer. And we're going to focus on 2-layer here because 2-layer is the hardest. A lot of people think more layers makes it harder. More layers makes it much easier. So it's a misconception. Smaller layers, harder problem, or less layers, harder problems for an Autorouter to solve. So solid line, top layer. Z0, and you can see if you hover Z0. Bottom layer, Z1, okay? And then there's this other type of like weird dash. So there's this non-uniform dash. What that means is there is a layer transition. So if I look at one of these points, this one is Z0, and if I look at this point, it is Z1. So what that means is that there needs to be a via because its exit layer, it needs to go into a hole and out on a different layer because its exit layer is different than its entry layer. So the unravel determines the optimal sort of positions, keeping the segment that you're entering on constant. It flips things around and it picks layers to minimize the risk that we're not able to solve, because the more vias we have, the less likely we'll solve it. So we'll look at an animation of this in a second, but I want to show that sometimes there are nodes with no risk at all. So yeah. Oh, okay. I'm remembering now. So if a node has no risk, then it actually doesn't have a box. So every box you see, every colored box, is actually a node with some level of risk. We can see here these two lines, this node has no risk, and the reason why is these lines are on completely different layers. There's one dashed and one solid. So Z0 and Z1. And that means that there's just no risk of them ever touching. There's no vias or anything like that. It's not going to be a hard problem to solve for later stages. So that is a 0. So that's kind of at a high level what unraveling does. It moves things around to select the optimal position. If we look at it animated, it'll be a little bit more clear exactly what it's doing. And especially as you start to learn what these lines mean, it starts to become very clear how this works. So I just want to throw some things out there. The Unravel Autorouter, we're at the start of it now, before we were at the end. So it hasn't optimized yet. We have higher risk here, 0.06 now, as opposed to 0.04. And we can see that we have some lines crossing, right? So maybe it'll find a way to unravel, to uncross those lines by changing the entry point position within the nodes. We have another cross here, right? So there's another cross. Maybe it'll be able to get rid of that. There's another cross here, and this has an 18% chance of failure because these nodes have to cross on the same layer. So we might figure out how to undo that, right? How to make it so that solves properly. And our Autorouter optimizes for not failing. That is the most important thing, is to not fail. It's fast and it tries to never fail to get full connectivity. So because you can always optimize, but it's very hard to get something that actually passes. So let's start taking a step through. I'm going to do deep viz. So it has selected this node to optimize. Let me see if I can. I'm going to have to remember how this works a little bit actually with the deep viz. Okay. So this will be a good example. So how the Unravel Autorouter works, and there's a couple of really good visualizations for it, so I'll have to go into the sidebar and find those good visualizations. But basically how this works is these red nodes indicate, the kind of red circle, indicate things it's going to try changing. And what it's going to do is, do you see how it's flipping lines and it's highlighting things in red? It's changing them. It's varying them to alternate configurations that are also still create a valid circuit, but maybe have lower risk. And the whole time it's doing this, it's running a star in the graph it's creating to try to find the right optimizations. Okay. And we'll look at specific solvers, but we can just animate that and we can see it's trying a lot of different combinations and it's isolating to specific sections. So it's not solving for everything at a time, using the same thing as the multi-section solver. It uses the same thing as the multi-section solver where it, let's go back to it just so we can have it up while I'm talking. It does the same thing as the multi-section solver where it picks a node. It says that's a high probability of failure node. I'm going to create a section and then I'm going to try to optimize that section by flipping things around without changing the boundaries of the section, without changing how the section connects to the larger circuit. So that's kind of how the unraveling works. We should, I'm going to look for a minute here. We should be able to find some specific unravel single section. So we have unravel single section, unravel multi-section. So we can look at both. Okay, so this is so for every solver there's going to be dedicated visualizers that help with just debugging that specific solver. That's almost always going to be there, and we can kind of look at this test case and see it really change the circuit until it gets rid of that crossing or optimizes for it. And I wonder how long. So eventually it found a zero risk solution. That's pretty cool. So at the beginning it was this, which is high risk. These are crossing on the same layer. And then when we solve it, it actually has basically a zero risk solution. There's no crossing because it was able to move this to the bottom layer and move all the layer transitions somewhere else. So very, very good solution. There should be some. So if we go to the single section solvers, this is more like showing you how to kind of like play with us. You can look at single section solvers and you can actually see some stuff around the scoring. So it's looking at every solution and the cost of it, and it's graphing that cost as it goes. And then I believe it's also showing the candidate. I think I played too quick. So it's completely solved now. But if I just take a couple steps, we can see it's got this list of candidates. And these candidates are defined by the changes. I can click on them. They're defined by the changes that they're performing against nodes. So this hash has a meaning and it grows as you make modifications. But basically, it's saying like, okay, if I construct a hash with each mutation I made to the graph, and score that mutation and try to find one that's better. So pretty simple. And I believe this might also fall into the framework of the hyper parameter solver or something like that. So we might be running multiple single section solvers in parallel or something like that. It doesn't matter to some extent, because when you're debugging an issue with the Autorouter, you usually can isolate, like, why didn't this section solve? You can really dig down and isolate. You don't have to worry about the grander vision at some point. Or the grander like scheme of optimization. But that is the unravel stage in a nutshell. It's a very unique stage for tscircuit, but it does result in a more optimal configuration for when we go into high density routing. Okay, we are now going to take a look at the 12th phase here, the high density route solver. The high density route solver, also sometimes called the detailed phase. This would be the first phase that people might consider, oh, it's a general autorouter. This is what most autorouters do. What we're doing is we look at a node and we just try to solve for the traces within that node. And because nodes never have any obstacles between them, we have to solve for it, or we can solve for it without worrying about any obstacles. Just how do we make these traces connect without any of them touching? At least unless they're supposed to be connected, right? So sometimes you can have different paths that actually are allowed to connect if for whatever reason they end up crossing and they're part of the same net. So this is the high density phase. This is the output of the high density phase. The high density phase is, it has the most solvers dedicated to it, but no one solver is that complicated. We just try a ton of stuff in parallel. So we run, if you were to introduce a new solver for the high density phase, we would just add it to the list of solvers that are running when we run high density, and iterations would be allocated to it automatically, and it would just run. So there are a lot of high density routers. I really can't do it justice in one video. But let's look at just the problem for a second. So I'm going to go into the high density section. I'm just going to click around randomly. This is a particularly hard high density problem, but this is the high density problem in a nutshell. You have all these traces and you know what layer they come in on, because all these previous phases solved for the physical position where it would enter a node, and we know where it exits. So this purple color, I think it exits up here, or no, I don't know where it exits. But it's source trace 20, so I could hover over these and figure out where it exits. Maybe there. Yeah, it exits here. So we know it enters here, exits there, and we just need to connect it without touching other traces. Simple. It's the simplest phase to describe. We just need to connect all these lines together without them touching. So there are a lot of examples of the high density solvers, many animated examples as well. And I believe as you get into the more later examples, the visualizer actually gets a little bit better. And you'll also see that it starts to get, they're different scales, right? So this is only 3 millimeters across. So this is a very small space. You'll also see with the high density solver, you'll sometimes see all these numbers on top. This means that we were trying different parameters using a hyper solver. We were trying many different parameters of the same solver. So the most common parameter is called a shuffle seed parameter, and that just says try routing the traces in a different order. So there's lots of things that you can try to kind of play with the high density router. So this is an example of a high density router that succeeded. We were looking at a lot of failing routers. So it had to connect these two lines, and it ended up finding this solver 14 worked very well. If we scroll down, this is a hyper solver, and it's allocating iterations to solvers that are performing the best, right? And if I click over here, I can see the parameters of the solver. So cell size factor. This is actually a grid solver. All these little dots kind of indicate where the grid is. The grid isn't explicitly shown, but but it is a grid solver. So cell size factor, these are smaller cells, I guess, or we're shrinking it down 0.5. And then some penalty factors and stuff like that. So these hyperparameters are varied to just try different stuff. It's kind of almost like saying, hey, try solving it in all these different ways and see what happens. So these will vary the internal A star, G, and H functions. So they'll create variations on that. And you'll almost always see the shuffle seed whenever you have anything you have to do in a certain order, right? So other autorouters use this thing called rip and replace, where you route, and then if two things cross, you try to rip them up and replace them with ones that don't cross. We don't really do that. We just vary the order and have hyperparameters. It just works better when you aren't doing global routing all the time, which many autorouters do. Which is bad. So this is kind of like our grid solver. And because it was the first solver, a lot of times you'll see it like just called the high density solver because it was the original approach, right? And just like the other phases, dashed line indicates the bottom layer. So I think even if I hover over this, you can see Z equals 1, and then actually, I think there's overlap. Yeah, it's a little hard. Z equals 0 for this purple one. So, and then the circles are the vias, right? So these are the holes where it goes under the board. And this is our grid-based solver. There are a lot of different high-density solvers, but the two that work really well are this one. I wonder what this is. I don't know what this is. High density suite. It just looks like another high density solver, again with the grid. There's really two types of very interesting high density solvers that are used most of the time, that are successful most of the time. One is the grid solver, that's very good. And then the other, especially on very condensed problems, is the what we call the HD polyline solver. These names, unfortunately, are just like whatever happened. We've tried so many, like 20 different solvers. So these are just the names that stuck around. But you can see this one, especially in animation, it looks pretty cool. But it basically like guesses where vias will go, and then it uses force-directed graph to optimize, to try to get sort of a route where there's no collisions. Okay, so let's speed this up and see if it ever solves, because we're looking at, I guess, a bunch of ones. Yeah, I guess this one never solves. Let's see if we can find one that solves. This one eventually solves, right? So at this point, it's saying, okay, we're meeting the where I guess vias are allowed to go outside the box slightly or something like that. So we've met enough of the criteria. The traces are far enough apart. The vias are far enough apart. There's enough space in here. Oops. There's enough space in here. By the way, if you hit the D key, sometimes you have to hover out, hover back in. That's really annoying. We should be able to, let me see actually. Oh, I think this is, for whatever reason, I can't measure here, but normally you can hit the D key and measure between these points. I don't know why it's not working on this particular visualizer. I think this is in canvas mode because in the normal mode, you can just hit D and you can measure the distances, so you can get in there and see like, oh, are those far enough apart and stuff like that. But anyway, this is a really big high density solver. They all implement the same kind of class interface. So if you have an idea for a high density solver, if you see problems that aren't being solved online, you can try to introduce a new one for high density solving. High density solving is arguably the most important problem in the autorouter, because if all the other stages do a poor job, high density solving can save it. But because you're kind of stuck with the conditions, the high density solver is stuck with the conditions, it can also receive impossible problems. So getting the high density solver good is important, but it doesn't solve the problem completely. Really quickly, I'm just going to animate the high density solver so that we don't lose track of everything. So that's the unravel phase. So now if I animate, we can see it happens so quick. But basically each node, I think, is solved per step. So it just goes very, very quickly. But that is the high density phase. And next up, we are going to do optimization. Some data cleanup. The remaining phases are pretty easy, but they're basically just post-processing. So at this point, by stage 12, you basically have something you could actually ship. And we used to ship, we definitely ordered PCBs without any post-processing. You can see they're a little bit messy looking. They're jagged, and the stitch solver is going to help with that. And they also don't connect all the way to the end, so the final touch has to be added. But for the most part, you have a board routed at this point. Lots of post processing to improve it, but the Autorouter has basically done its job for the most part, and everything else is just post processing. Okay, if you've made it this far, good job. Now we're going to talk about the stitch solver. So the stitch solver it's more of a data phase. It's not really solving anything or doing anything super important or opinionated. It's mostly just kind of fixing the trace routes to make sure that they connect to each other. It's kind of making them more global because each node kind of only worried about its route. So now it's combining all of them together. There's a lot of things that can get messed up and historically have gotten messed up. So this kind of cleans the data. So for example, you need to make sure that the points along each trace, even as you go through all these nodes, are always in the same order. You need to make sure they connect all the way to the start and the end. And this phase is very simple. It's literally just going through each node and connecting the points together and making sure they connect to the final destination. So this is just a simple data processing phase. There's not a ton going on here, but you might run into a weird case or something. Maybe a route's wrong, or I can't imagine what would go wrong, but that's what the stitch phase does. All right, we are now going to post-processing, removing useless vias. So removing useless vias is a phase that you can see it's executed twice, actually, which maybe is not really the right way to set up this pipeline, but it's run here and it's run here. And it's run after simplifying the path, because sometimes simplifying the path can mean more vias are removed. So you could actually run this quite a few more times. So it should probably be aggregated into a single phase or something like that, where we can choose the number of iterations or something like that. But yeah, removing useless vias. Let's take a look at it. So this is going to be step 14, and let's see. So what we're looking for is between 13 and 14, are any vias removed? I actually think for this example, I don't see any vias getting removed at all. So let's go to keyboard 4. That's a great one for testing. It takes a while to run, so I'll be sitting here talking for a while. But how useless vias works, they truly are useless vias. So you're looking for points in the route where a via was inserted, but there's no reason to go under. There's no reason to create a hole. And that can happen because earlier phases were like, hey, just to be conservative, we're going to put a layer here. We're going to make you change layers just to make sure that the traces are as separated as possible. And now that we're through high density, we can say, actually, there's no reason to be that risk adverse. Let's move it back up because we've already figured out that a route exists, so we can move it back up. So let's step on over to that phase, and we will try to find a useless via. I wish I had stats set up for it. I don't think that this phase has stats. It's a good contribution. Yeah, there's no stats for this phase, so we should probably track it. It'd be good to see it. But so we're going from the stitch phase to the useless via phase, and it's kind of hard to see the vias in the stitch phase because the stitch phase does this really weird highlighting. But basically from 13 to 14, yeah, I see one. Okay, so in this path, you're never crossing anything. So there's no reason for this via. And this makes sense that this would happen because these are so far away, and the unravel and all of those things, they work so locally. They don't think about traces that are separated by this distance. So there's no reason for this via. And so it's removed, and that's it. Super simple. Removes useless vias that were for some reason created, maybe due to conservativeness of earlier phases. And that's it. That's the useless via removal phase. It's run a couple times. There's great visualizers for it. I don't know if we can pull one up. Useless. It might also be called something else. Via removal 1. So it looks like this is the keyboard example, and we've got a via that doesn't need to be there, so indicated by these 2 lines. Sometimes for some reason the vias aren't drawn or whatever. Possible PR to fix the visualizer there. Good contribution. So it identifies the 3 sections, looks at the vias. Oh, actually, it's running through the entire via solver. So if I look up the oh yeah, okay, this visualizer is not as useful as I thought. It's a good isolated example, but it's not a single path removal. Maybe this one will be a single path removal. Yeah, this one is a single path removal, so it's not the most exciting visualizer, but you can see that it made them all the same color, all the same choice. So sometimes that the algorithm is easy, we don't spend as much time on the visualization, and this was definitely a case of that. And removing useless vias is fairly easy. So easy post-processing stage. Okay, in this video, we're going to look at how the code for the capacity or the initial pathing solver works, which I guess is a type of capacity pathing solver. So again, it's the thing that takes a pair of points and kind of runs an A-star algorithm to connect those points together through these nodes. And when we went over this last time, we could see that there was on each node being explored, there are this G cost, the heuristic cost, which is an estimate on the remaining cost, and then the F, which is a weighted sum of those 2 things. So really just G and H is all you need to worry about. And so G means, the sum of all the costs that have come before, and H means the estimated cost of the future. So that's going to be important. I'm going to jump right into the solver. So the solver used in this phase extends this capacity pathing solver. So this is kind of a base class for all of them. You can get the actual solver class just by looking at the active stage in here. So, if I refresh this, I go down here, hit play, I can see the active stage. I can also hit deep viz and step through it to see if there's any subsolvers. I don't think there's any subsolvers being used. Let's go. Whenever you're looking at a solver, just go to the step function. It's the easiest way to go. I was looking at this earlier, and this is a misnomer, so I'm just going to rename that right now. So we have a current connection. So we're just looking at our current connection, and as we go through them, we'll increase that index. So we're looking at that current pair, right? So there's this red line. So this is the current connection that we're looking at. And we've got a list of candidates. I guess that's handling for if we don't have the list yet. We're sorting the candidates based on F. So we're hitting the candidates with the lowest cost first, or the lowest estimated cost, because it's G and H together. We get the next candidate to evaluate. So this is in this case, I don't think it shows current candidate, but let's pretend that this is the candidate. What we're doing is we're saying, okay, let's take a deeper look at this candidate. Let's see where this candidate can go. Maybe we're almost at the end, right? So you're just doing that kind of A-star exploration. Again, if we look at pathfinding.js and we animate this, can I reset? Oops. Whoa, no. I don't know how to, sorry about that. I'm leaving it in though. If I start search again, it's like you always have one square you're advancing at a time. Even though it goes very fast and it seems like it's expanding evenly, you're always really looking at one node at a time, and that would be the next candidate, the one that has the highest ROI, the one you think is closest to the end or has the lowest cost. You're going to look at that. So this could also be called the best current candidate, right? This is the one we think is closest to the goal, is the right way to go based on those cost functions. So we get that current candidate, and then we see, okay, is it connected to the end? If so, we're done. If not, we're going to get the neighboring nodes and add them to our candidate list. So try to expand outward further. And this is how basically every A-star solver works. But this one, it has, and I think in this repo, all of our A-star solvers work like this. We have a compute G and a compute H function, right? And so compute G is always going to compute the cost of the path so far. And then compute H is always going to estimate the cost into the future. And then here's our calculation of F, which is a weighted sum of these things. So this greedy multiplier is a hack to make A-star act less optimally, but go much, much, much faster. Okay, so you don't really need to worry about that. If you're familiar with A-star, a lot of times they don't teach this kind of concept of a greedy multiplier. It's called many different things. It's called weighted A-star in many cases. You can completely ignore this other than it makes A-star go faster and on occasion not do something optimal, but usually it ends up being optimal anyway. And there's actually a bound of how non-optimal it can get. So it's a very good compromise if you want to go fast. Lots of speed increase and very low decrease in optimality. So compute H is kind of the interesting function here. How do we compute how much estimated distance there is? And in this case, for this base class, we just compute a simple distance for the between the nodes. And then to compute the G cost, we just say, okay, what's my cost to the previous node I was at, and add that to the cost to get to that previous node. So very, very simple G and H functions for this kind of graph exploration. And I think the actual class being used is this thing called capacity pathing greedy solver. So it looks like this solver really only differs in that it always, so there's a function, does node have capacity for trace, which presumably is just a check, and it's saying I always have capacity. So this solver, because in the initial pathing phase, we don't really want to block any solution because they'll be optimized later. I guess we found that just saying, hey, it doesn't matter if a node doesn't have capacity, let it through is a good option. You could also override this function to say, hey, if the capacity is getting too negative, like we really, really don't have capacity, you could return false, but then you risk never finding a solution. And I think with the initial pathing solver, we just always want to get a solution. It's an approximation because in the next phase, we're going to optimize that path. If we scroll down, in the pathing optimizer, we'll optimize those paths. So it's not really that big of a deal to get a bad path. We'll optimize it. Get node capacity penalty. I guess that's a way of getting a penalty, presumably to the G, to the G and not the H, but I'm not sure how it's used. So we're penalizing based on the node capacity in some way. So maybe this biases it to kind of explore routes that don't go through other nodes. So lots of ways to kind of tweak this to get good initial paths. Having good initial paths speeds up later phases, paths. But basically in a nutshell, that is how the initial pathing solver works. In the next stage, we'll talk about the pathing optimizer in the next video. Okay.